All right, thanks for joining me today. We're going to go over covalent bonding. Up to this point, we've mainly been going over ionic bonding, but covalent bonding is a little bit different. We're going to learn how to write and name them and just kind of contrast and compare them with ionic bonds. So I want to differentiate covalent bonds from ionic ones, and we want to understand the rules for writing and naming covalent molecules. A little bit of vocabulary, which is covalent and diatomic. We'll hop right into this. Remember, you can always pause and rewind if needed. So covalent bonds are things that hold together two nonmetals. You can see in the image that we have over on the corner, a couple of examples of covalent molecules would be water and ammonia. You can see that water is H2O. Most of us know that. Ammonia's got nitrogen and hydrogen. And again, these are nonmetals. This is different than in ionic bonding because in this case, the electrons tend to be shared with one another. There's still kind of the same goal here, which is to get to 8 electrons. If we remember back and we think about valence electrons, oxygen has 6 electrons. You can see that they're yellow in this picture over here. Hydrogen has 1, and we've got 2 hydrogens here. So again, if we add all these numbers together, 6 plus 1, we get our magic number of 8 to get a full shell. And you can see that they're overlapped here instead of being transferred like we've seen before. And the other image we have over here with ammonia, can get this out of the way just a little bit. Maybe not. It's fighting with me here. All right, so nitrogen has 5 valence electrons. You can see them in red. And then each of the hydrogens has 1 valence electron. So we put all those together and we still get a full shell of 8. And again, that still ends up being the same goal as we've had with our other bonding with ionic. It's just a different way of doing things. A couple ways to remember this is usually the prefix co means together. And if you see the ending of this word valent, it should remind us of the word valence, which is referring to the outside shell electrons. So we're kind of just putting the valence shell electrons together to make a new molecule. A little bit of a rewind, comparing and contrasting that to ionic bonds. Ionic bonds was a metal and a non-metal. So eventually when you're asked to name or write formulas, one of the key differentiation between the two is that ionic bonds are still going to have a metal in them. Covalent bonds will not. The thing with ionic bonds is that the electrons were transferred. In other words, they were gained or lost. So we might have a metal who's going to be losing an electron. We might have a non-metal that's going to be gaining an electron. That's going to cause a difference in charge. That difference in charge is going to cause an attraction to one another. Typically, ionic bonds form solid compounds like table salt, NaCl. And a lot of these compounds that are created end up having a really, really strong bond. They have high melting points. This is not always the case, but typically ionic bonds are going to be stronger than covalent. So let's go back to covalent. One of the things about covalent is they tend to make up most of the things around us that are necessary for life. Sugars, fats, oils, proteins, DNA, propane, methane, ethane, ethanol, alcohols. And you can see in these images, these models, they can form really, really long chains because they just continue sharing. And carbon atom, for example, can share 4 electrons and make bonds in 4 different directions. And they can just have almost an infinite number of ways that they can be put together. Ionic bonds and ionic compounds, not quite so much because they tend to form crystal structures and it has to do with the positives and negatives and just kind of everything canceling out that way. One group of covalent molecules are called diatomic. These are typically gases and halogens. You can help remember this, the prefix di means 2, atomic obviously means atoms, and these are things that bond with themselves. There are 7 of them. They form a number 7 on the periodic table with the exception of 1. So the pictures you have over here kind of show how they would be put together, but 7 of these make up kind of the number 7 if I can do a decent drawing on the periodic table. So if we have our halogens, starting with fluorine, and then if we move over a couple of places and add nitrogen and oxygen, you'll see that they kind of make the shape of the number 7. This is only 6 of the elements, so the other one ends up being hydrogen, again, is on the other side of the periodic table. But there are 7 of them, and 6 of the 7 actually kind of make the shape of a 7 on the periodic table, with hydrogen being the other one. So again, these atoms or things like we breathe with oxygen and nitrogen gases around us. They bond to themselves. They share electrons with one another. If we're breathing oxygen in right now, you're not breathing in oxygen, just elemental oxygen. We're breathing in two atoms of oxygen that are going to be bonded together in a diatomic molecule. If we were to need to write this out, we would just call it oxygen. There's no fancy name with it or anything like that. Right. When we name binary covalent compounds, binary means two. One of the things we have to do with covalent ones is we use prefixes. We don't use prefixes with ionic ones. And so we do have some rules for putting these together. Now we probably need to learn and memorize these prefixes. Most of them are not new to you. There's a couple on here that are new that we don't use very often, or we don't use outside of science very much. So tetra would be for 4, hepta would be for 7. Those are two of the ones that typically see people struggling with. The other ones you've probably seen before: mono, di, tri, pentahexa. These are geometric things. Octa, like an octopus. Nana, we don't use much, but it looks like the number 9. And deca for 10. A period of 10 years is a decade, so it's the same prefix that we have there. So if we have a covalent compound, we have some rules for being able to write the name of it properly. Right? So simply we write the name of the first element, just write it down, and then we stick a prefix on it to indicate the number of atoms that we have, unless there's only one atom. So if there's only one atom, we don't use the prefix mono to tell how many we have. So let's look at a couple of examples. For example, H2O would start off the first name, and we know this is water, but if we were doing it more scientifically, the first part of this would be dihydrogen, because we've got 2 hydrogens. And so just as a reminder, when we put the 2 after a number, that's a subscript, that's telling us how many hydrogens we have. So if we have 2 hydrogens, we write di for 2 hydrogen, and that tells us literally that there's 2 hydrogens. Something a little bit different that you're probably familiar with, CO2 is carbon. So CO2 would start off just with carbon. We write the name of the element, which is the rule. We put a prefix if there's more than one. In this case, there's not more than one, because this 2 only goes with the oxygen. This is 1 carbon, so we don't write monocarbon, we just write carbon. Now doing the second one, we write the root and use the IDE ending similar to what we would do with an ionic compound. And in this case, we always use a prefix. Right? So we write the root, we give the IDE ending, and then we always end up using the prefix. So going back to our 2 examples where we had H2O, then if the H2 is dihydrogen, the O is monoxide. So we write the IDE version of oxygen, oxide, and then we put mono in front of it. With monoxide, we end up kind of sticking 2 of the O's together instead of making it monoxide. And then CO2, the O2 again is oxide, but since there's 2 of them, in this case, it's going to be carbon dioxide. So if we practice naming some things, put these things together, again, our rules, we just write the first one here. So we would start this off with, my pen is not always cooperating here. This is not good at all. So this is carbon, and then with 4 of these, let's see if I can go slowly, tetra for 4, and then chloride to finish it up. 1 sulfur, I just start off with sulfur. 3 oxygens, trioxide. 2 nitrogens, so I'll write dinitrogen. 1 oxygen, monoxide. So that's how we would write those, by following the rules that we've been given. Now, if we go the other way around, how do we write a formula given the name? Again, we use subscripts to tell how many of each one we have. Unlike with ionic, there's no charges, there's no crisscrossing. So again, carbon dioxide, I would just translate that to being 1 carbon and 2 oxygens. We would write it CO2. Diarsenic trioxide would be 2 arsenics, 3 oxygens. So I go to the periodic table, make sure I get my symbols right. So 2 arsenics, put a 2 after the AS, 3 after the O. A little bit of practice. Put these up here. Sulfur hexafluoride, carbon monoxide, all kinds of fun sounding things. So that's just one sulfur. Hexa is 6. Fluorine, fluoride is fluorine. So I would write F with a 6 beneath it, and we're done with that one. You got to know your prefixes though. Carbon monoxide, that's 1 carbon and 1 oxygen, which is just C and a capital O. And then tetrasulfur, that's 4 sulfurs. And then dinitride is 2 nitrogens. Come on, pen. That's it. And this one, unlike ionic, we would not reduce the 4 and 2. We leave it the way that it is. Covalent molecules we never reduce the fractions, if you want to think of it that way, because it's not really a ratio. When we did ionic ones, there was a ratio of elements one to another. In this case, it's not a ratio; it's an actual number. So tetrasulfur dinitride would have 4 sulfurs and 2 nitrogens. We wouldn't reduce the 4 and the 2 down to 2 and a 1 to make it simpler. We would leave the formula the way that it is, like this. All right. So in summary, covalent bonds are when we share electrons. There's no rules on pairing them. Like you can have carbon and oxygen, make carbon monoxide. You can also have it make carbon dioxide. And this is why we have to end up using the prefixes to name them, because they can come in multiple different ways. You need to be careful when you're given an element to name, because if I ask again, or someone asks again, what is the name of MgCl2, it's really easy for someone to say, well, this is going to be magnesium dichloride, but we need to remember that magnesium is a metal. And if magnesium is a metal, then it's an ionic bond. And if it's an ionic bond, we don't use prefixes. This would still just be regular magnesium chloride. So when you're working with ionic and covalent, that's usually the first thing that you really need to do, is to decide, is it ionic or covalent, and then use the rules that follow based upon that. So always check to make sure that there's a metal, or if it's all non-metals. All right, thanks for joining me. Hope that was helpful.